In the last video, we were given the first derivative of a function, and we wanted to know where the original function was concave up, concave down, and had points of inflection. In the last video, we calculated the derivative of the function and kind of got it as clean as we could. So why don't we analyze the function now? And we'll use the first derivative test in order to find out where the graph is concave up, concave down, and has points of inflection. Here. All right. So the first question is, since this is a rational function, I've got something in the denominator. Are there any points where this is undefined? Are there any vertical asymptotes in this function? Well, there would be vertical asymptotes anywhere that the denominator was equal to 0. So that's x squared plus 3 quantity cubed. Is that ever equal to 0? Well, it would be if the thing inside the parentheses were ever 0, but that's never going to happen because x squared is always 0 or more, and so adding 3 to that, this is always going to be a positive number. Okay, so we don't need to worry about the function being undefined anywhere. So the next question to ask is, where is the second derivative equal to 0? So that's going to happen anywhere that the numerator is equal to 0. So 36 times x plus 1 times x minus 1, that's going to be 0 when either x plus 1 is equal to 0 or x minus 1 equal to 0. So x is equal to plus or minus 1. All right. And so why don't we take a look at when x is not plus or minus 1. What's the derivative going to be? Is it going to be positive or negative? So what I'm going to do is I'm going to put out a little number line here. And these are going to be the two critical points that I'm thinking about. So I've got a -1 and a +1. So everywhere in this interval, it's going to be the same sign. Everywhere in this interval, it's going to be the same sign. And everywhere in this interval, it's going to be the same sign. So let's double check to see what it is in each of those values. All right, so what we're going to do is the first derivative test says we're just going to take some representative point from inside this interval. Like from this middle point, let's pick 0. So if x is equal to 0, then g double prime of x is equal to 36 times x plus 1. 0 plus 1 is 1. 0 minus 1 is -1. All of that over x squared plus 3. 0 plus 3 quantity cubed. So 3 cubed. So is that positive or negative? Well, we've got a positive number, and a negative number we're all multiplying together. So the numerator is going to be negative and the denominator is positive. So this is negative. In fact, we didn't even need to put in the numbers at all. I could have just said positive times negative over negative, because all I'm interested in is the sign here. So this is negative. So over here, the second derivative is negative. So this is concave down. All right, let's pick a point over here in this interval and see if it's positive or negative over here. All right, so let me pick x equal to, I don't know, 5. Pick some big number. All right, so if I plug 5 into here, once again, I don't care what the number is. I only care if it's positive or negative. So let's just look at the signs. So I'm multiplying 36, which is a positive number, times 5 plus 1, which is a positive number, times 5 minus 1, which is a positive number. And I'm dividing that by x squared plus 3, which is a positive number, cubed. All right, so I'm multiplying a whole bunch of positives and dividing it by a positive. So the second derivative is positive everywhere on this interval. So this is concave up. All right, and the last bit is we'll pick a number over in this interval. So again, may as well pick a big number, something where I don't need to think too hard. And then once again, we're just going to look at the signs. So 36 is a positive number. X plus 1, negative 5 plus 1 is a negative number. Negative 5 minus 1 is a negative number over negative. So this is a positive number. This is positive 25 plus 3 is positive 28 cubed. So positive times a negative divided by a positive. Is that positive or negative? We have an even number of negatives here, so they're going to cancel each other out, and we're left with a positive response there. So this is concave up. All right, so that graph is going to let us answer the question. So we're going to determine the intervals where the graph of g of x is concave up. So g of x is concave up on, first is going from negative infinity to negative 5 and positive 5 to positive infinity. All right, so these are both open intervals, and concave down on negative 5. I'm sorry, I've been saying negative 5. The actual endpoints here are 1 and 1. I apologize for that. And it's concave down from negative 1 to positive 1. All right, what about points of inflection? So these were both values where the second derivative was 0. Are they points of inflection or not? Well, here we're going from positive to negative. So this is going from concave up to concave down. So this is a point of inflection, and this is going from concave down to concave up. So this is a point of inflection. So there are points of inflection when x equals negative 1 and x equals positive 1. All right, so that's how you take the derivative of a complicated function like this, and then we're analyzing it to figure out over what intervals. So we think about where the dividing line is, which is the points where the second derivative is equal to 0, which was just setting the numerator equal to 0 and solving. And then for each one of those 3 intervals that the rest of the real number line is broken into, we just need to pick one sample number and test whether it's positive or negative. So since it's negative at 0, it's going to be negative everywhere in that range. Positive everywhere over here, positive everywhere over here. In the next video, we're going to be looking at a new rule called the second derivative test, which makes things a little bit easier in some cases, maybe not easier in other cases. It's just another arrow in our quiver that we can use to test for if something is a maximum or a minimum. And we'll see what the second derivative test is, and then we'll look at an example where we try finding maximums and minimums using both methods, and you can get a sense of the differences between them.